All right, good morning, everybody. Today is Wednesday, April 15th. Thank you guys for getting your assignments done. Hopefully, like I mentioned to you yesterday, you had a good break and kind of ready to just keep making progress here. I know this is weird, but the further that we do get through the calculus book, I'm anticipating probably all you guys or most all of you, you're just, the further we get, the better off you're putting yourself as far as when you run into this stuff in college, okay? So we're going to continue to sort of just motor along. The only thing that's going to be particularly weird about the remainder of the school year is, you won't be taking any calculus tests, okay? But we're going to try and push through as much of the material, the content that we can get through, okay? So what we've been looking at for the last week or so has been the first and second derivative tests. First derivative test is how we determine critical points that represent maximum and minimum values of a function's graph. And then the second derivative test goes on to identify points of inflection where curvature or the concavity of a graph changes. What I have here is I have the actual notes for section 4 down, okay? Because section 4 is basically where we take, it's called optimization problems. We've run into that word optimization before. Optimization comes from the word optimize or optimum. Okay, and optimum means basically ideal. So when we start thinking about this, there's a whole lot of this stuff that we're really not going to go through. And I know it's a little bit probably harder to follow along with me when we're going through something like this as opposed to when I'm actually writing and you can kind of decipher what exactly the steps are as we go through them. But if I were to try and write these down, what you'll notice is the examples are more like word problems, even though they're not really context problems, okay? They're not like story problems. They're just written out in words rather than as equations and stuff like that. It just would have taken a long time to navigate this if you'd have been kind of following along in the typical sense, okay? So what we're doing right now is we're trying to optimize, which means find ideal situations, okay? So if we really want to think about story problems, we've talked about it before, that the ideal circumstance depends on what it is that you're exactly talking about. For instance, money is one I always go back to. There are different types of ideal circumstances for money. Sometimes you want to maximize money. Sometimes you want to minimize money. And the easy situation is the difference between income and debt. You want to maximize your income while minimizing your debt. They both represent dollars and cents, money, but it's totally different scenarios. So in essence, what we're doing is we're looking for maximums and minimums. So like I said just a minute ago, the first derivative test is the test that we perform to find critical numbers that represent maximums and minimums, okay? That's what we're going to be doing, but we're going to be setting up functions or setting up equations ourselves, okay? So Ms. Buchholz here has a lot of different guidelines, a lot of different kind of explanations, but I think if we just dive right into the first example, you can kind of make sense out of this, okay? Again, it's not a story problem, but it's a word problem. It says the product of two positive numbers is 288. So what we're going to do is we're going to use these word problems to set up our own equations, okay? And let me grab my pen here so I can point a little bit easier. We're trying to find these two positive numbers. So what we always do with these story problems is we define our variables. We'll let x be our first number, let y be our second number. And when it says the product of two positive numbers is 288, we have that equation right here, and they're written out as primary and secondary. It really doesn't matter that you label primary and secondary equation, but that you take that sentence and write it as an equation. The product of two numbers is 288, so x times y is 288, okay? The next equation is an equation for the sum of the second number and twice the first number. So here's where you'll see that. The sum of the second number is y, plus twice the first number is 2x, but our primary equation, it doesn't tell us what that sum is. It says the sum of the second number and twice the first number is what we want to minimize. So you'll notice that we don't set that equal to anything, but instead we just set it equal to a capital S for sum, okay? And what we're going to do then is we're going to bring this sum function, S equals, we're going to bring it down right here, S equals 2x plus y, We're going to do some basic substitution, some algebra 1 substitution, and then we're going to differentiate. So here's where you'll see it. S equals 2x plus y becomes S equals 2x plus, and then we use our secondary equation to replace y. If you divide by x on both sides from this secondary equation, you'll get y equals 288 over x. And then you substitute y out of the sum function, and you replace it with 288 over x. This is just a simple system of equations that we've worked with countless times, starting literally in 7th and 8th grade math, is where you do just basic substitution, okay? But now we have the sum of these two numbers, or these two situations, twice the first number plus the second number, but rewrote the second number as 288 divided by x. And now what we can do is we have this sum function. All we have to do is differentiate once to find the critical numbers of maximums or minimums, okay? And one other thing worth mentioning is this. There are going to be certain constraints that you might want to keep in mind today. The original problem said both numbers have to be positive. That means bigger than 0. So when we differentiate, so here's s equals 2x plus 288 over x. The derivative of the sum function is going to look like this. The derivative of s with respect to x. So instead of dy dx, we'll write it as ds dx. But then you just differentiate the sum function according to the x's. So the derivative of 2x is 2. If you move this x up there with 288, it would be 288 x to the negative 1. So negative 1 times 288, that's the negative 288. X to the negative 1 would become x to the negative 2, but then you move that back down to the bottom where it becomes x squared. So here's the just simple derivative. The derivative of s with respect to x is 2 minus 288 over x squared. The critical numbers here would be 0 is a critical number because you can't have 0 in the bottom of this fraction. But so would positive and negative 12. Because if you plug 12 in right there, it's 12 squared is 144. 288 over 144 is 2. 2 minus 2 is 0. Okay, so just set the function equal to 0 and solve for x. You get positive or negative 12. So according to our first derivative test, we have 3 critical numbers. Negative 12, 0, and positive 12. But remember, it said that the critical numbers have to be positive. So that eliminates, we don't even need to do this whole, this whole test basically for our numbers here. We don't need to find x as one of 3 numbers. It's the only critical number in the domain that makes sense. 0 and negative 12 are out. That means 12 is the only remaining critical number. We really don't even need to plug this in and figure out if it's decreasing and increasing to figure out that it's a minimum. 12 is the only critical number that makes sense here. So x has to be 12, which means we can plug that back in to right up here. 12 times y equals 288. Divide 288 by 12 and you'll have y. Y is 24. So x is 12, y is 24. Okay? Hopefully you were able to follow that. And I'm going to give you guys full disclosure here. I have no idea if this is going to be one of those assignments that you breeze through real easy and have no questions, or if it's going to be one that you're going to have it re-explained before you can even start it, okay? We'll have to just see, all right? But let's look at 2 more examples that Mrs. Buchholz gives us here, okay? All right, so this is not part of this next example. It's right in here is all the work, okay? It says find 2 numbers whose product is negative 12. So again, you'll notice we're letting x be one number, let y be the second number. Don't worry about this, let s equals sum to be minimized. Right here, 2 numbers whose product is negative 12. X times y equals negative 12. And then if we isolate y in that equation, meaning divide by x, you'll get negative 12 over x. So that's right here. Y equals negative 12 over x, coming from the product equaling negative 12. Okay? It says the sum of whose squares is a minimum. So we write out an equation for the sum of the squares. The sum is equal to x squared plus y squared. So it's the sum of the squares. And what we're going to do is we're going to minimize that sum again. Okay? So what you'll see here is this. It's x squared plus, and in place of y squared, they bring down negative 12 over x squared. They clean that up by doing the squaring. It's 144 over x squared. And so basically here's our sum function. S equals x squared plus 144 over x squared. And then we differentiate. So the derivative of s is, the derivative of x squared is 2x. The derivative of 144 over x squared is negative 288 over x cubed. Again, where that would come from, I'm just going to write it off to the side here. Positive 144, if we move the x up with it, so positive 144 x to the negative 2. Negative 2 times 144, that's the negative 288. Okay? And then, so negative 288, drop down the exponent, it becomes x to the negative third, but then you move that underneath. So that's where this x cubed comes from. Okay? The critical numbers here, if you set this equal to 0, the only critical number that we can actually have is, well, actually I take that back. The critical number obviously here would be 0. Okay, so if you have a critical number being 0, then obviously you'd have a 0 in the denominator. Down here, you'll notice they take the whole thing, 2x minus 288 over x cubed, and set it equal to 0. Okay, so trying to just double check how exactly they did this. All right, they moved the 288 over x cubed to this side, multiply by x cubed on both sides, that moves it over here. 2x to the fourth equals 288, divide by 2, x to the fourth equals 144. So here's the deal. At this point, you'd have to do the fourth root of 144. Well, the square root of 144 is 12, but if you do the square root of 12, you get an irrational number, okay? That's not gonna necessarily fit into two numbers who are gonna give us a product of negative 12. So since this is gonna give us an irrational number, a square root that doesn't come out nicely, 0 is our only critical number that makes sense in that scenario, okay? Yeah, that's kind of weird. Okay, that one she kind of just left incomplete, but basically you would say x equals 0, and then you could plug that back in. Well, that's going to be kind of weird because 0 is going to give us... Let's not worry too much about that one. That's kind of an odd example. Okay, let's go on to one that makes a little bit more sense because you don't get 0 as one of your critical numbers. Okay, let's actually go with this one off to the side. All right, and we'll call it good once we get this one. It says find two positive numbers where, okay, so x is my first number, y is my second number. They obviously have to be positive numbers, so if I get critical numbers that are negative, I don't have to worry about them. It says the sum of the first and twice the second is 24. So here's the sum of the first, x, and twice the second, 2y, is 24, and its product is a maximum. So you have to, whatever you're trying to maximize, you label that P or S or whatever it is. So P equals, how do you write the product of the two numbers? X times Y. What you'll notice here is this. They rewrite this, X times Y equals P, as X times 12 minus 1/2 X equals P, because if you take this equation and you isolate Y, you get 12 minus 1/2 X. Okay, so you have to do this solving for y, substitution, and then end up with this, a function only involving x's so that you can differentiate. When you distribute x, you get 12x minus 1/2 x squared. The derivative of that is 12 minus x. If 12 minus x equals 0, then you subtract 12, divide by negative 1. That means that our critical number is 12. That critical number is my x value. If it is 12 right there, 12 plus another 12 is going to equal 24. So 2 times y has to be the other 12. So y has to be 6. Okay? Now I know I breezed through that relatively quickly, but I wanted to keep the video at a relative minimum. Okay? Ultimately, what you have to do is you have to set up a primary equation and a secondary equation. The primary equation is the one that you're trying to minimize or maximize. So it's going to tell you a word to minimize or maximize. If it says the product is a maximum, you use the letter P, and then you set up the equation based on how you find a product. Similarly, if it says the word sum, like this, Here's the word sum. You use the capital letter S, but then you write the sum of whatever it says. Up here it was the squares of the numbers. So it's x squared plus y squared. Okay, then you do just algebra 1 substitution to replace whatever y is with something in terms of x. You end up with a singular function with only x's and whatever you're trying to optimize, and then you just differentiate it to find the first derivative critical numbers. Okay? So I'm going to leave it at that. Like I said, I have no idea if you guys are going to just breeze through this assignment with no questions, or if you're going to need me to, look at a couple of them again tomorrow and re-explain it, because it was kind of weird just trying to follow along while I kind of speed talked through this, okay? So give the assignment a shot, see if you can get your answers to mesh with the back of the book. If you can't, let me know. Don't freak out over it. If you need clarification, I'll give you clarification tomorrow or later on today, depending on when I get all your questions, and then we'll go on from there. Okay, guys? Alrighty, have a great day, and we'll talk to you later.